And today I'll talk about the graph coloring, Biclique partition, and communication complexity. This is based on joint work with my PhD advisor, Benny Sudakov. So in graph theory, one of the very elegant, very beautiful theorem was proved by Graham and Pollack in early 70s. It's actually one of the earliest applications of linear algebra in combinatorics. They showed that if you have a complete graph on k vertices, and you want to partition the edges into edge disjoint union of complete bipartite graphs, then you need at least k minus 1 such complete bipartite graph. By complete bipartite graph or Bicliques, I mean you just take two disjoint subset of vertices, and inside each subset there's no edge, and between them there are like a complete thing. So you just connect everything between them. Okay, it's really automatic. So now I'll show the example that this is tight. For example, you can look at k equals 5. So you have complete graph on 5 vertices. And one way to partition into 4 Bicliques is you just take all the edges from the first vertex, and then you take all the remaining edges from the second vertex, and you keep doing this, then you get 4 Bicliques. But you might ask, is this the best possible? What happens if in the beginning I don't take the edges from the first vertex, but instead I take a k2, 3. So let's start over again. So I take this complete bipartite graph, and then I take another one. Then you see we still need at least 4 Bicliques. And there are several proofs of this one, and one of my favorite proofs was due to Weber. And it's actually very short, I can explain it in one slide.
Bipartite graph, complete, with all edges, everything.
Yes, all edges. So now let's prove it by contradiction. Suppose we can partition the edges into less than n minus 1. So it's n minus 2 Bicliques. Then we immediately get the following identity here, this identity, by assigning to each vertex a variable xi. Now we can rewrite the right-hand side into the 1/2 of the square of the sum minus the sum of the squares. Then we try to take the left-hand side to be 0. The natural way to do it is we just take those sums corresponding to Li and make them 0. And then I also take the sum of all the Si to be 0. Then if you plug all these equalities in, you will see the left-hand side will vanish, and the right-hand side only has the term minus 1/2 times the sum of squares left. Now we have n minus 1 linear equation and n variables. So we know there exists a non-trivial solution. So if we plug it in, we get 0 is equal to the negative the sum of square, which is smaller than 0. So we get a contradiction. I really like this proof. And actually there are maybe 3 or 4 other proofs of this Graham-Pollack theorem. And it's quite surprising that although this theorem looks very combinatorial, but all the proofs we know is kind of using some eigenvalues or matches, or the Sylvester law of inertia, all these kind of things. And there's no purely combinatorial proof, no. And for a long time, people believe that if there exists a combinatorial proof, maybe the important parameter of the graph that will give a lower bound of the minimum number of Bicliques you need is just the chromatic number of this graph. So the chromatic number of the graph is just the minimum number of colors you need for the vertices, such that every 2 adjacent vertices receive different colors. So based on this speculation, Noga alone, Michael Sachs, and Paul Seymour made this following conjecture in the early 90s. They asked, is it true that if an edge set of a graph can be partitioned into edge disjoint union of k Bicliques, then the chromatic number is at most k plus 1. So Graham-Pollack theorem basically says that this conjecture is true when the graph is a complete graph. And it can be considered as a bipartite analog of the very famous open problem in graph theory by Erdős, Weber, and Lovász. If a graph G is the edge disjoint union of k copies of complete graph, each has size at most k, then the chromatic number is at most k. And this is still open. Now you see a difference here is instead of looking at the Bicliques, we look at the cliques of size at most k. Okay. So now if for my convenience, I just define the Biclique partition number to be the minimum number of Bicliques you need to partition the edge of G. So alongside Seymour conjecture says that it is true that the Biclique partition number is always at least the chromatic number minus 1. And people have been working on this problem for like almost 20 years. And well, a natural way to attack is try to prove some lower bound in the chromatic number. So very easy bound you can get is just log the chromatic number. Here, this is not only true for the Biclique partition. Even if you look at the covering, this is true. It basically uses that the chromatic number of the union of two graphs is at most the product of these two chromatic numbers. And Murray and Bisch-Wernerson improved this lower bound to 2 to the power of square root of log. This is greater than 2 to the log. And Alon Havil proved the same 2 to the square root of log lower bound using communication complexity. I will talk about this later. And there's another group of people, they verify this conjecture for all the graphs with chromatic number up to 9. They somehow reformulate this problem and change it to such that you only need to check finite number of cases. Okay. So our main contribution to this conjecture is that we actually show that there exists an infinite family of graphs such that the chromatic number can be greater than the Biclique partition number to the power of 6/5. So we get a counterexample to this conjecture. And it also gives actually not only the chromatic number is greater than Biclique partition number, but it gives a superlinear gap between these two parameters. So someone may say, okay, so somebody gives us a conjecture and give a counterexample and so what. But this is not the end of the story. So actually, if you can find a better counterexample in the sense that there's a bigger gap between the chromatic number and the Biclique partition number, you might be able to solve some important problems from communication complexity. That's what I'm going to talk about next. So here I need to introduce the two-party communication model. This was first studied by Andrew Yao in 1982. Suppose we have a publicly known known Boolean function f. It's a two-variable function from s times y to 0, 1. And it has a matrix M. So matrix M basically corresponding to the value of f. Now we have two people, Alice and Bob. Alice only knows some element from x. Bob only knows some element from y. And what they want to do is they want to evaluate the value of f at a point x, y. What they can do is they can exchange the information in bits. So every round, Alice can tell Bob one bit of information, and Bob can tell Alice another bit of information. They keep doing this. They stop until they know what f of x, y is. So one trivial way to do is Alice just tell Bob what x is, right? Because we know the function f, then Bob just plug in and get the value of it. But actually, this is often not the optimal way to do it. So that's why we need a definition of so-called deterministic communication complexity. It's the number of bits needed to exchange in the worst case by the best protocol. So there was a theorem by Melhon and Smith in the 80s. They showed that for any Boolean function f, the deterministic communication complexity of f is always at least log the rank of the matrix M. And actually, people believe that this lower bound is not very far away from the truth. So Lovaas and Sachs made the conjecture that the deterministic communication complexity can be upper bounded by polylog the rank of the matrix. So the best lower bound known, I think, is due to RV and norm. It's like log the rank to the power of some 1 point something, right? Log 3 maybe. So this conjecture, log rank conjecture, is still open and is closely related to a rank coloring problem in graph theory. So a long time ago, there was a conjecture in graph theory saying that the chromatic number of any graph is at most the rank of the adjacency matrix of this graph. But it was later disproved by Noga-Alon and Posimo. And actually, Lovaas shows that if you have a graph and it has large gap between the chromatic number and the rank of the adjacency matrix, then it will give a separation between the deterministic communication complexity and the log rank lower bound. So in order to improve the lower bound for the deterministic communication complexity, we just need to get a graph with very big gap between the chromatic number and the rank. And very similar to this connection, alongside Seymour conjecture. So let me remind you what it is. So it's like study the Biclique partition and the chromatic number. So it's also closely related to the so-called non-deterministic communication complexity for clip versus independent set problem. So in the two-party communication model, suppose we have a publicly known graph gamma, and we have S is a family of cliques, Y is a family of independent set. So clique is just every two vertices are connected, and independent set is just every two vertices are not adjacent. So Alice now knows a clique C from X. Bo knows a clique I from Y. What they want to do is they want to know whether the clique and the independent set intersect. So basically, they want to evaluate the function f of Ci equals the size of the intersection of C and I, which is obviously either 0 or 1, because if you take the intersection of a clique and an independent set, you still get both a clique and independent set. So either has no vertex or just 1. Now, the non-deterministic communication complexity is defined as log C of f, where C of f is the minimum number of monochromatic combinatorial rectangles needed to cover actually the 0 entries of the matrix F of F. Now, this is not the original definition of it, but it's like a definition that is more easy to understand in mathematics. So Yanakaki showed that the non-deterministic communication complexity of this problem is always lower bounded by log m. This is basically by looking at, you take the single vertex as independent set and clique, and this will give us a unique matrix, which is like m by m. So we need at least m combinatorial rectangles to cover it. And now the upper bound is the square of log m. This is by some kind of algorithm which needs at most log m run every run. Alice tell Bo or Bo tell Alice one vertex, so it takes log m bits of information. Now there's a very nice relation between the Alonso-Seymour conjecture and this complexity. So we can actually show that any separation between the chromatic number and the Biclique partition number will give the separation between the non-deterministic communication complexity of this problem with the log m lower bound. So it's very similar with this connection between the rank coloring problem and this log-rank conjecture. So if we use our counterexample to Alonso-Seymour conjecture and this proposition, we can get improve the lower bound just by a constant 6/5. But remember that our construction is like the Biclique partition number is greater than the chromatic number. The chromatic number is greater than Biclique partition number to the power of 6/5. So you can see in order to really get square of log m, we need like a more exponential gap between those. Not exponential, exponential. Okay. So exponential. Okay. Now, so before the end of the talk, I want to address like two questions. So the first problem is it true that we can find a graph such that the Biclique partition number is m, but the chromatic number is big enough, so that using this proposition, we can show that the non-deterministic communication complexity is lower bounded by the square of log m. So the second thing I want to work on, I've been working on this for a while, but it's a very kind of hard problem, so I don't really have an idea to solve it. So it's this Weber-Lovász conjecture I mentioned in the very beginning. So is it true that if you take the edge-decision union of k cliques, each of size k, then the chromatic number is still k? So this is known that the chromatic number can be at most 1 plus little o1 of k by Jeff Kahn. But I think the precise version of this conjecture might have some, if you can find a proof, maybe it can be nice and have some interesting application in computer science. Okay, I think I will stop here. Thank you.